let's dive into a real scientific detective story, one that took decades to solve. It's all about a revolutionary kind of supersteel that, on its face, seemed to break the laws of physics, all because of a secret hidden deep down in its atomic structure. So who's the star of our show? It's a material called nanostructured Bainitic steel. Now this isn't just your run-of-the-mill strong steel, it's a whole new class of material. It's made using a special heat treatment that creates this unbelievably fine internal structure. We're talking about tiny platelets of steel that are just 20 to 40 nanometers thick. Insanely small. And when I say strong, I am not kidding. This stuff can handle pressures over 2 gigapascals. To put that in perspective for you, that is more than 3 times the strength of the steel they use to build skyscrapers. But you know, its crazy strength? That's not even the weird part. The real puzzle is what's going on inside. Okay, so to get this strong, the steel needs a certain amount of carbon. And here's where things get weird. According to everything scientists thought they knew, there's no way it should be able to hold that much carbon. It's kind of like trying to dissolve a whole cup of salt in a tiny glass of water that should only hold like a teaspoon. It just shouldn't work. And that was the paradox that had scientists stumped for decades.
So to really get to the bottom of this, we need to zoom in, way in, on 2 key players at the microscopic level: a form of iron called ferrite, and a carbon-rich material called austenite.
Okay, so check this out. The official scientific rulebook says that the ferrite part of the steel should only be able to hold about 0.02% carbon. But when they actually measured it, they found concentrations up to 0.2%. That's 10 times higher. So the carbon was definitely there, no question. The problem was, for ages, nobody had a clue how that was even possible.
Right, so for a long time, the scientific community had what they thought was a pretty good answer. The thinking went something like this: the extra carbon wasn't supposed to be there, so it must be getting trapped somehow.
This idea is called the Cottrell atmospheres theory. Basically, picture an iron crystal. It's not this perfect, neat atomic scaffolding, right? It's got little flaws, tiny misalignments called dislocations. And the theory was super simple. These extra carbon atoms were just getting snagged and trapped in those defects. Seemed to make sense.
And I gotta stress, this wasn't some wild fringe idea. No, this was the textbook answer for decades. If you asked a materials scientist about this, they'd point you right to Cottrell atmospheres. As far as anyone was concerned, case closed.
But then, technology happened. We built tools that let us see things atom by atom, and suddenly what we found completely blew that old theory right out of the water.
The game changer was this incredible technique called atom probe tomography. Think of it like a super precise atomic scalpel. It literally shaves off a material one single atom at a time and then maps out where everything is in 3D. It was the first time we could actually see where every single one of those carbon atoms was hiding.
And what they saw was, well, it was a total shock. That extra carbon, it wasn't bunched up around the defects at all. Not even close. It was just hanging out, totally dissolved and evenly mixed within the perfect, flawless parts of the crystal. The main suspect in our mystery, the trapping mechanism, had a rock-solid alibi. It was wrong.
So this just blew the whole case wide open again. The question wasn't, how is the carbon trapped anymore? Now it was, if the rules say the carbon can't be here and it's not being forced to be here, then maybe the rules themselves are wrong. But how could that be?
To solve this, scientists had to think completely outside the box. They stopped focusing on the carbon atom itself and started looking at its home, the iron crystal. And they asked a radical question. What if the crystal itself isn't the shape we've always assumed it was?
Okay, let's unpack that. Normally, we think of this iron structure, ferrite, as a perfect little cube. It's called body-centered cubic, or BCC for short. All the old rules, they're based on that perfect cube shape. But the new idea was, what if, in this supersteel, it's not a perfect cube? What if it's what's called body-centered tetragonal, or BCT? The easiest way to picture it is just a cube that's been slightly stretched out.
And it turns out there's a known way this can happen. It's called the Bain strain. When you cool the steel down really fast, the atoms don't have time to just leisurely rearrange themselves. Instead, the whole crystal structure just kind of snaps. It gets compressed in one direction and stretches in the others, instantly changing from its original shape into this new stretched-out tetragonal one. And this right here was the big aha moment. The whole paradox only existed because everyone was playing by the rules for a perfect cube. But what if the playing field was different? What if the crystal was actually this stretched-out tetragonal shape? Maybe, just maybe, the rules for how much carbon it could hold were completely different too.
Now, that's a fantastic idea, but a hypothesis is just a guess without proof. The challenge now was to actually see it. They needed a way to measure the shape of these tiny nanoscale crystals and confirm that they were in fact stretched.
So how do you do that? You bring in the big guns. Researchers went to a synchrotron, which is this huge, powerful particle accelerator that creates some of the most intense X-rays on the planet. By blasting the steel with these X-rays, they could analyze the pattern they made when they bounced off. That pattern is like a fingerprint that tells you the exact distance between the atoms. Basically, it let them measure the crystal's precise shape.
And the results were crystal clear. They crunched the numbers and compared the data to 2 different models. Now, this chart shows something called a poorness of fit score. Basically, the lower the number, the better the model matches reality. As you can see, the standard cubic model, not a great fit. But the tetragonal, stretched model, it was a near-perfect match. This was undeniable proof. The crystal was not a perfect cube. This was it, the smoking gun. It was the very first piece of direct experimental evidence that proved the hypothesis was right all along. The atomic structure of the ferrite wasn't cubic, it was indeed tetragonal. It was stretched.
And once they had that confirmation, everything else just clicked into place. Now that they knew the crystal's true shape, they could finally figure out what was really going on and solve this decades-old carbon paradox once and for all.
So the next step was to basically write a whole new rulebook, but this time for the stretched shape. They ran these powerful computer simulations to calculate how much carbon this tetragonal structure could actually hold. And the answer was a total game changer. It turns out this stretched-out shape can hold way, way more carbon than the old cubic one.
Okay, so let's recap the whole thing. That super fast cooling process, it forces the iron crystal into this stretched tetragonal shape. And that stretched shape happens to be a much more comfortable, geometrically perfect fit for carbon atoms, so it can just naturally hold about 10 times more of them. The carbon wasn't some unwanted guest being trapped. Nope. It was a welcome resident in a house that was literally shaped just for it. And just like that, the paradox was solved.
You know, this whole mystery, which lasted for decades, existed because of a single fundamental assumption, that this crystal was a perfect cube. Questioning that one idea didn't just explain this one supersteel, it literally rewrote a fundamental chapter in materials science. It really makes you wonder, right? What other rules of science are we all following just based on assumptions we've never even thought to question? What's the next big mystery just waiting for the right tool to come along and crack it wide open?